So this simulation, let me first do a couple of things and then go back. So one is the simulation that I said that I would show. So here, for example, is the random graph on so here I have taken a particular graph. So let me just run it. So here there is a graph with 6 vertices and some edges, you see. So this letters are a bit small. So this graph is pictured here. So, and you see the sequence of steps. It started at 1, then it goes to 4, which is one adjacent vertex. Then it goes to 6. From 4, it had 3 possibilities. It happened to choose 6. Then from 6, it went to 5. Then it came back to 1. Now again, it makes a choice. First time when it was at 1, it went to 4. But now the choice, it chooses among 4 neighbors and it goes to 6, which is here. Then goes to 1. Then goes to 6. Then goes to 4, etc. So one of the interesting things that we will study, if you like, you can think about it. So after which vertices will be visited more often than others? So if I run this for a very long time, will it visit vertex 3 more or will it visit vertex 2 more? So over a long run of this Markov chain. So that is one of the type of questions we are going to answer in the lecture. Okay. So this is just an illustration. I had this animate, but for some reason, whenever I run it, it seems to be causing problems. So I will not run that animation. So then the Ehrenfest chain also, somebody had written that the Ehrenfest chain was not so clear. So maybe I will just illustrate here. So you may recall that Ehrenfest chain. Let's just go back to the example. So Ehrenfest chain, there are these n states or n plus 1 states from 0 to n. The state is how many molecules are on the left partition of this one. And what is happening at each time, you can look, if you can forget about the gas motivation if you want, and just think that wherever you are in this 0 to n, you will move to the right. If you are at location I, you will move to the right with probability n minus I by n and to the left with probability I by n. Okay, so that's what will happen. And at the end points, it will be from 0, it will always go to 1. From n, it will always go to n minus 1. So what happens to this chain? The motivation is coming from this gas example. So here is an illustration of that Ehrenfest chain where n I have taken to be 40 states and I run the Markov chain first 20 steps starting from the location 0. Okay, so it starts at 0. This is time. And this is the states. Okay, the states are 0 to 40. And it started at time 1 at, time 0 or time 1. Time 1 at 0. Then it went up, it is kind of oscillating. So this is when I run the Markov chain for 20 steps. Okay, but what if I run it for a bit longer? So 200 steps. So you see, it went and somebody asked this question, will it equalize? Okay, so there are 40 molecules. Will it become 20-20 at some time? You can see that at already after about 50 or 70 steps, it hit 20-20, meaning both were equal. So this 20 means left side partition has 20 molecules. So it hit that. And after that, it seems to be hovering around that middle. Okay, so let's run for much longer. What if I run it for 2000 steps? So you see, it went and it very quickly went to the middle where almost equal and it's kind of hovering around that. Okay, it's sometimes going a bit below. Sometimes there were only 10 molecules on the left, but mostly it is hovering around 20. This is one of the behaviors that we will be very interested in. As I said, what is the chance that in the room, 75% of the molecules will be on one side and 25% will be on the other side? So that sort of question. So this is the Ehrenfest chain illustrated here in this graph. Okay. Okay. So then let me go back to the lecture. So before continuing to the next one, so there is a sort of modeling type question. Somebody had put it on later. It came on the chat box. So let me answer that. Somebody asked. So this Markov chain has. So this what I'm going to explain. If you don't catch what I'm saying, ignore it. It is okay. Not relevant to what we count. But somebody asked, so this has only one memory, right? It uses the idea is that the where xt plus 1 will be, the probabilities depend only on the location of xt, where I am now. But what about using more memory, like I was using in the language situation, where I was keeping track of previous 2 characters, 3 characters, 4 characters, and so on? Can we extend the memory? Do we need new definitions, like Markov chain, maybe Markov 2 chain, Markov 3 chain, etc.? Actually, it is not necessary. It turns out that if you want longer memory things, it can also be modeled and on Markov as Markov chain. So, for example, so this I'll just make a remark. As I said, feel free to ignore it if you don't get what this is. So, suppose y1, y0, y1, y2 is a sequence such that it has memory 2. That is probability y. Okay, for some reason, why is it not writing well? Okay. Sorry, I will erase and write again. So it has memory of 2, let us say. Okay. Probability that yt plus 1 equal to j, given y0 equal to I0, and so on up to y sub t equal to I sub t. Suppose it depends not only on this but on the previous one also. So let us say it is some function, let's call it q, which depends on the previous 2 states and j. So in our situation, it depended only on the current state and the target state, whereas here it is depending on 2 things. This is not a Markov chain. But you don't need a new theory to study this. What you can do is you can, so this is some s valued. So this is s valued, taking values in s. So what you can do is you can define x0 to be y0, y1, x1 to be y1, y2, x2 to be y2, y3, and so on. Okay. So these are tuples, but mathematically, what is it? It is just s cross s valued random variables. Okay. Now this is actually a Markov chain. It is a Markov chain. Its future will depend only on the previous one. Okay. I will leave that as an exercise, but you think of it. Suppose you know what happened up to time 1. That means you know x0 and x1. That means you know y0, y1, and y2. Now you can, since you know y0, y1, and y2, based on y1 and y2, you can tell what are the probabilities of y3. So, and y1 and y2 are there in x1. So that means the distribution of x2 will depend only on x1 value. So this is actually a Markov chain in our definition. So for longer memory, you do not need a new theory. You can model it using this Markov chain definition itself. You just have to enlarge your state space. Okay. So I will now go to the next point. So, okay. Multi-step transition. So let us do, so far we have only given examples and so on. So let's do some calculation in general. Okay. So let's write down, let x be, let be a Markov chain with state space S, which we can take to be always, usually we take to be 1 to n, and transition matrix P I comma j coming from S. It's an n cross n matrix. Okay, suppose we have this Markov chain with this transition. Now, where x0 is starting, that I will always fix. So x0 could be random. So see, Markov chain, my definition only involved how to go from one step to next step. So what about x0 itself? We will take x0 to be always fixed. You can make it random. Nothing is gained by doing that. So let us say we have some favorite location where we are going to start from, some I0. Okay, I0 belongs to the state space. So now what do we know? So let's calculate. So let's do some simple calculations. Okay, I want to ask what is the probability. So I will write. So what is the probability that x1 is some particular state I? Okay, so I will write here I0 to remind myself that this means that x0 is I0. So this subscript here means what is x0. I will indicate by writing p sub I0. Some people prefer to write probability x1 equal to I1 given x0 equal to I0. Both are okay. Okay, I will just for simplicity write like this. So what is this probability? Okay, well, we know that it is at state I0. So from I0, it has to immediately go to I1. So that probability is given by the transition matrix, which is entry, which is P I0 to I1. P I0 I. That's all, right? So very simple. Let's do one more. What is the probability starting from I0 that x1 is some, let's say, I and x2 is some j? Okay, what is that probability? Well, if you think about it, so first it is starting at I0, it has to go to I. So that probability will be P I0 I. But having come to I, what's the probability it will go to J? Now it is at I, so it has to go to J. So that is P I comma J. Okay. So P I0 I, P I comma J. So if anybody is pedantic about how did this come, I just am saying something. So what I am doing is that I am writing this as probability x2 equal to j, x1 equal to I, given x0 equal to I0. Henceforth, I will appeal to intuition and write these things, but for once I will show how did it come from the definition. So we can write this probability, this is just the notation, that's all. I have written in a different notation that given x0 equal to I0, what's the probability? X1 is I and x2 is j. Now you can write it as probability x2 equal to j, if you know what conditional probability means, if you understand the definition of conditional probability, then you can write it as conditioning on x0, conditional probability given this, and multiplying this event which we have pushed into conditioning, namely x1 equal to I given x0 equal to I0. Now, all these are told to us by the definition of Markov chain. So this is exactly P I0 to I1, P I0 to I. That is what this is. And this is by the definition of Markov chain. If you remember, so what is the definition of Markov chain? That whatever be the previous states, the probability that you are going to be in J at time t plus 1 given all the past depends only on the last state and Pij. So that's what I'm using here. So to say that this is actually going to be P, previous state means is x1, so Pi to J. Okay, so that's exactly what, so this is getting multiplied and that's what I have written here. Okay. So this is telling us what we can write down the probability for any trajectory. Okay. So if I write P I0 suppose I write a much longer thing. X1 equal to, I want at time 1 to be at state I1. At time 2, I want to be at state I2. And so on up to at time t, I want to be at state I sub t, let us say. Okay, t can be 10 or 20, whatever, it doesn't matter. So how do we write the probability? Again, you can break it into conditional probabilities like this, conditioning each step. And what will you get? It is intuitively very clear. From I0, you have to go to I1. That probability is P I0 to comma I1. From I1, you have to go to I2. So that probability is P I1 comma I2. And then from I2, you have to go to I3, P I2 to I3, I2 comma I3, and dot dot dot. What is the last step? It is xt minus 1 here is I sub t minus 1. It has to make the transition from it minus 1 to it. So you will have P sub I t minus 1, comma I sub t. Okay, I hope it is distinct enough what I have written. So this is how you write for any particular trajectory, you can write down the probability. This is what is going to be the probability of that. Okay, so for example, just going back to these pictures, for example, let's look at this graph. What is the probability if I start at 5? What is the probability that I first go to 6, then go to 2, then go to 4? Okay, suppose we want to calculate the probability. From 5, I'm starting at 5. I want to calculate probability to go to 6, then 2, then 4. So we just have to multiply the probabilities transitions each time. So from 5, chance to go to 6 is, since there are 4, we have a 1/4 probability to go to 6th. And having come there are again 1/4 things. So 1/4 probability to go to 2. And then from here, 1/3 probability to go to 4. So 1/4 into 1/4 into 1/3. That will be the probability to go from 5 to 6 to 2 to 4. Okay, so that's what I have written here in generality. So this is how you write. Okay, so I hope this point is clear. Everything depends on this. Now, the interesting question. So this one can do. Okay, so the interesting question, in fact, this will be the key question we will be interested in. But for now, let's ask, suppose I don't care where I am in intermediate steps. Okay, so the question is, what is the probability? So question. Fix some t greater than equal to 1. Okay, what is the probability that starting from I0, that at time t I am at some state j? Okay, so this is the same as for those who prefer conditional probability notation. This just means xt equal to j, given that at time 0 I am at I0. Okay, or let's just make I0. Okay, so what is this probability? How do we find that probability? For example, let's go again to that example. So suppose I start at in this picture, in this graph, so I start at 5 and I want to go to, let us say 1 after 2 steps. What is the probability that after 2 steps I am at 1? Now there are multiple ways that could happen. I could go from 5 to 6 to 1, or I could go from 5 to 3 to 1. Okay, 5 to 6 to 1 will have probability 1/4 into 1/4, because 1/4 into 1/4. 5 to 3 to 1 will have probability 1/4 into 1/2. So we have to add I'm now not interested in where I was in between. I'm only interested in the final location. So then I have to add over all trajectories which lead to that final location, right? So what do we have to do? So we can do this probability. So now I start calculating this probability, just like I illustrated there. There were 2 paths. Here, what are all the paths which can lead from I0 to j in t steps? Okay, maybe I go from, so I have to sum over all trajectories. What are trajectories? Maybe from I0 I go to I1. From I1 I go to I2, and so on up to I sub t minus 1. There, I don't care where x1 is in I1, x2 is in I2, xt minus 1 is in it minus 1. They can be anywhere. The point is, I have to go from I0 to I1. Okay, and then from I1 to I2, and so on up to Pi t minus 2 to I t minus 1. And in the last step, I have to go from I t minus 1 to j. Is this sort of clear? So let me maybe I write one special case just in case I'm not making myself clear. So let's say, for example, if I wanted Pi0 x2 equal to j, that means x1 can be anything. This is Pi0. X1 can be anything. X2 can be j. So I have to sum over all possible states for I. All possible states for x1. So I sum over all I in S. That I don't care where I was in x at where what x1 is. I only want x2. So that will give me sum of Pi0 I1, because this we have already calculated. Pi0 I and then Pi j. Okay. So that's exactly, that is the t equal to 2 situation that I have written. More generally, I sum over all possible, these things run over all possible states. So this I1, I2, IT minus 1, they run over all possible states. Okay, so this is the answer. We have to sum over all the trajectories of the probabilities. But can we recognize this as something? Okay, so the thing is this, look at this here, Pi0I, Pij, summed over I. What is this? If you look at this Pi0 to I, Pij, I say it is like this. It is you multiply the matrix P with itself twice and take I0, j entry. Okay, so this is the square of the matrix power. Okay, so I'm multiplying P with itself like a matrix and take the I0, j entry. What is the I0, j entry? How do we get the I0, j entry? So P square means we are writing P11 up to P1n dot Pn1 dot Pn, n. So the I0 row, so if I want to multiply P with itself, I take here another copy of P, P11 dot up to Pn1n, and then here Pn1 dot Pn, n. So now how do I get a particular entry? If I want the ij entry of the product, what should I do? I should take the ith row, or since I write here I0th row here, and I have to take the jth column here, right? So what is in the I0th row? Pi01 dot up to Pi0n. What is in the jth column? P1j dot Pn, j. What do I get when I take this row and multiply that? I get Pi01, P1j, Pi02, P2j dot that, and that's exactly what I had written here. This sum is precisely how you multiply matrices, right? So that is what P square, it is just, so if you want to know after 2 steps what's the probability to be at j starting from location I, you just take the P square and the ij entry of that. So what will this be? So this will be analogously, you can think about it. So if it's not immediately clear, you think about it, okay? So it is just the same as taking the product of P as matrices n times, or sorry, t times. That's not n. N is for me the number of states. This is P to the power of t. I0, j. So this is I0, j entry of the tth power of P to the t, the tth power of that matrix P. Okay, so that is what gives you the probabilities of after t steps. If you want after 5 steps, you need p power 5. If you need after 10 steps, you need p power 10 and so on. So this is a nice thing. So because it's kind of, so if you are kind of understand linear algebra, etc., it's a little kind of interesting, because when we wrote this transition matrix in the beginning, in the definition of a Markov chain, when we wrote the transition matrix, it was just an array of numbers. To call it a matrix, you can call it a matrix if you want, but it has no geometric meaning. It has no linear algebra. There is no vector space, nothing. It's just a way of writing a table of numbers. But now we see that what you learned as matrix multiplication actually plays a role in calculating probabilities. Or you can turn it around and you can give this as a motivation for why you multiply matrices like this. Matrix multiplication is a little bit of an odd way. When you multiply matrices, you don't multiply entry by entry. You do this strange thing. Take the ith row, jth column, do something. The way you learn why that matrix multiplication is useful in linear algebra is by substitution. Okay, if y is linear combination of xi's and zi's are linear combination of yi's, how to write zi's as linear combination of xi's? But matrices were invented multiple times, discovered multiple times in the history of mathematics and science. And one of the times was by Heisenberg when he was doing quantum mechanics. And he came to matrices via something very analogous to this. You can look at this as a motivation, if you like, for matrix multiplication itself. Anyway, that's just a side remark. But what we have found is we can find t-step transition probability. So this can be called t-step transition probability. What we were given was one-step transition probability. This is t-step transition probability. Okay. So all we need to do is raise the p to power t and then find the entry. Okay, so this is all that is. Okay, so the fundamental question we are interested in about Markov chains is the following. The main question. So we have solved it in some sense, but we have not really solved it. How to find this? This is not such an easy thing. Matrix multiplication itself is quite a complicated thing. So how can we find p raised to the power t and the ij entry? Is there some way to do it? So that is what I will now raise as I will call it the fundamental question. Okay. So take in that above situation, how can we actually find p to the power t ij entry when t is large? So mathematically, we will let t go to infinity. What happens to p to the t ij? That means I start this Markov chain at state I, and it has run for a very long time. What is the probability it is now at state j? Okay, so let's take this. That's what I was asking here. So let's take this random graph. The graph example. So here there is a graph. Now I start at some state, maybe 1. Okay. After a long time, is it more likely to be at 3 or is it more likely to be at 2? Okay. Can we tell that? So 1 is close to 3. So you may say that it is going to be more likely to be at 3. On the other hand, there may be other reasons why you say it is going to be close to 2. Okay, we don't know what will happen. So what would be your guess? You should think in this case, where are you more likely to be, at 3 or 6 or 2, which is the most likely place to be? Or if not just the most likely one, what are the chances to be in different states? Does it matter where I start? Or does it not matter where I start? Okay, so this is what we have to. So you would think that if it has been running for a long time, maybe you don't remember what happened, how you started. Maybe it doesn't matter at all. Okay, so that's kind of going to be the interesting thing. So let us do this example, which I just in the break I wrote one. So let's take this. Let's take a two-state example. Okay. So here I have this two-state Markov chain with alpha equal to 0.2. Alpha I have written as A and beta as 0.7. So the off-diagonal entries are 0.2 and 0.7. 0.8. This means from state 0, it goes to 0 with probability 0.8, 0 to 1 with probability 0.2, 1 to 0 with probability 0.7, and 1 to 1 with probability 0.3. Okay, so that is what it is, right? So now this is the one-step transition probabilities. Now let us see what happens after a long time. So if I raise matrix power 2, so that means after 2 steps, what is going to be the probabilities? It's going to be 0.78, 0.22, something. It happened. Okay, so this case. So let's run it for a long time. What happens? You see, something funny has happened that both rows are almost same, or actually exactly same. Okay, the entries are 0.777 and 0.222. That seems to be the case, and you can change p. So let's change p to a to 0.5 or something like that. Okay, so let's do that again. So now the matrix is slightly different, but you see again the rows have become same. When you raise this matrix to a very large power, it seems that the rows become identical. And you see that they add up to 1, 0.48 and 0.42, they add up to 1. So this is actually a stochastic matrix, but all the rows are same. What does this mean? So if you understand the interpretation of this, what is the 1, 2 entry here? This means in this Markov chain, after 100 steps, if I start from the state 0, after 100 steps, what is the chance I am at 1? It is saying that's the 1, 2 entry, okay, which is 0.41667. What if I start at state 1? Well, then I have to take the 2, 2 entry. That also is point. So it's saying that it doesn't matter what state you start in, you will get exactly the same. Okay. So this is a very general looking phenomenon. So let's just write down any stochastic matrix. Okay. So let's make a more complicated stochastic matrix, 3 by 3. Or yeah, okay. Let's maybe do this one. Let's do this one. Where is this? A is the adjacency matrix. Okay, here is a P. Okay, let me run this again. So what is the transition matrix for this particular one? I'm going to show you in numerically, and then we will try to prove it as a theorem. So I'm writing P in the matrix form. So it is looking like this. So the vertices from vertex 1, it can go to 2 or 5 or 3, right? So you see 2, 3, and 5 have 1/3, 1/3, 1/3, like this. This is the transition matrix of this Markov chain of simple random walk on this graph. Now the question is, what happens when I raise this? Let's make it numerical. So n of p will just make it numerical. So I don't need to see these fractions. So the probabilities look like this. Okay. So now what I want to do is I want to take I want to raise it to a large number. Okay. So let's say we run the Markov chain for 50 steps and see what the matrix looks like. You see, P had all rows were different in P, but when you raise it to a large power, all rows have become identical. You see, everything is 0.15, 0.2, 0.15, 0.15, 0.2, 0.15. What does this mean? Okay, so again, what is an entry here? For example, the 2, 3 entry here, the 2, 3 entry, which is 0.15, is what is it? If I start the Markov chain at state 2, after 50 steps, what's the chance it is at state 3? That probability is 0.15. And what this is telling is it doesn't matter where you start. You start in state 4. After 50 steps, you are in state 3 with probability 0.15. It doesn't matter where you start, you will be in those things. It's a very curious looking feature, which we need to explain. We have to make a theorem out of this. But this is an important point. So if at this point there is any question I would like to take on this specifically. Is there any? question on this? I mean, I am showing you some phenomenon which we are supposed to justify.
Yeah, Ricardo is asking what is the geometric interpretation of the space that the transition matrix is performing linear transformation on.
Yeah,
That
that
is
is
on what element is the transformation being carried out of?
very good. That is what I mentioned. So it is not, there is no geometry here. See, when we use matrices in linear algebra, it is something when with respect to a certain basis, but really on the back, there is a linear transformation on a vector space. So it's a geometric object. But here, it is not a geometric object. So for example, the 1, 2 entry has a meaning. It is, there is a state 1, there is a state 2, and P1, 2 is the transition probability to go from state 1 to state 2. Now, state 1 is important, state 2 is important. There is no meaning to state 1 plus state 2 by 2. Okay, that would be, if you were thinking of a vector space, we would have to take linear combinations of states. What is state 1 minus state 2 into plus 3 times state 5? What does that mean? It means nothing as Markov chains. Nevertheless, this matrix, nevertheless, this actually is useful. We think of this as matrix. So there's no linear transformation, really speaking, at the back of it. But pretending that using the linear algebra concepts is actually useful. That's what, so far we have seen how matrix multiplication is useful. We are going to see how eigenvalues of this matrix are also going to be useful. So there is no geometry apparently, but there is. Okay, this is all I can say. Any other questions?
Actually, someone has wrote, but I'm not sure at what point he wants to talk about. I can read it. Could we use the central limit theorem? So it
No, no, no,
was,
no, no,
so,
no,
yeah,
no, no.
no, that's
This,
what.
no, it is not related to central limit theorem. It is not the central limit theorem at all. Something else. Okay, so yeah, so but the phenomenon. So let me write down what we saw in simulations. So what we saw, what we have observed in simulations is this, or in the numerically, what we observed. That in many situations, at least in many or some, the P to the T matrix as T goes to infinity, it converges to a matrix Q. Okay, as T goes to infinity, it converges to a matrix Q whose rows are identical. Okay, it has some Q1, or let's call it a different one for a standard name is there. So for some reason, I'll call it that. So let's say there is a, okay, maybe I can call it Q, but the entries are, all the rows are the same. Okay, so let's say the first row I write as pi 1, pi 2, pi n. Then the next row is also pi 1, pi 2, pi n. And all the rows are pi 1, pi 2, pi n. For some, so instead of n square entries, there are really n distinct numbers. For some, pi I, which are greater than or equal to 0, and they add up to 1. That is what we see. We just showed two, three examples, but that is what seemed to be happening. But that would mean what? What would be the significance of such a statement? The significance of such a statement, what is the significance if it is true? Okay, so I have to move a bit. So for some reason, this is going all over the place when I try to write. Okay, so let me say, what would be the significance of such a thing if it is true? If true, that's right. That means we are saying that p to the t I comma j is approximately pi sub j for all I comma j, right? If t is large. So the limiting t going to infinity, if I interpret it for large t, it means p to the t I comma j is like pi j. But what was p to the t I comma j? We saw what p to the t I comma j is. It is a probability. It is the probability to start at I and be at j after t steps. That is p to the t ij. That means we will have obtained a very good answer to this question, that after a large time, the probability to be in various locations don't depend on where you start. See, the right side does not depend on I at all. That's what it means to say all rows are same. It does not depend on I. So irrespective of where you start, it seems that you will be in these states with certain probabilities j. Okay. So that is one feature. So what are the important things here? So this does not depend on. So this pi j does not depend on I. That means it does not depend on I. What that means is initial state is forgotten. Irrespective of where you start, it looks like the chances. But it also raises a question. What are these pi j's? Pi j's need not be equal. Well, for example, let's go back to that graph example we had. In this graph, where this is the graph, okay, this looks too symmetrical, right? No, this is not the same. See, what are the probabilities? For vertex 1, it is 0.15. For vertex 2, it is 0.2. So vertex 2 and vertex 5 have higher probability than vertex 1, 3, 4, and 6. Why would you say that is the case? Okay. So it's clear that this graph is so symmetrical. 1, 3, 4, and 6 look the same actually, but 2 and 5 look different. For example, the degree of vertex 1 is 3 of 1, 3, 4, 6. All of them have vertex degree 3, whereas 2 and 5 have vertex degree 4. They have 4 edges around them. So there are more ways to go to 2 and 5 than to go to 1, 3, 4, or 6. So it looks like that is what this is respecting. Okay, so but in general, what is that raises a question? So they may not be equal. How to compute? Because that is important. How to calculate? How to compute these numbers? This is the main question. Okay, so let me summarize what I said. I raised the fundamental question of finding long-term transition probabilities, but transition probabilities for t steps is p to the t ij, that is the entries of p to the t. So the question becomes, can we understand what happens to the powers of this matrix t as t becomes larger and larger? What happens to the entries? And numerically, we seem to see that in many situations, this converges to a matrix which has all equal rows, which would mean that there is a very definite answer to our question. P to the t ij converges to some pi j, which does not depend on I. But how to compute these pi j's? It's all a bit mysterious, and this is what we have to answer now. Okay. So now I will go on to answer this question. First, we will do with a simple case. It may spill out over to the next lecture also, which is okay. I will start with a simple example of two-state Markov chain. So let's work, but this is not always true. Let's observe that also by the way, straight away. But we observe numerically that this happens, but it's not always true. Well, why? When is it not true? For example, okay, no need to do this numerically. So not always true. So let's give two examples. Suppose P is a simple 1, 0, 0, 1. Okay, this is a transition matrix, stochastic matrix. Row sums are 1, entries are non-negative. What is P to the power of t? Is 1, It's identity matrix. However many times you multiply, you'll get back the same thing. So what is this telling? It is not converging. All the rows are not becoming equal. It's not writing well. Equal. Okay. And it's kind of what is this Markov chain? This is a Markov chain with two states, let's say 1 and 2. If you are at 1, you will stay at 1. If you are at 2, you will stay at 2. Nothing happens. It's the most boring chain. But you see that in this case, P to the T does not converge to a matrix of this form where rows are equal. This is not true. So because we can tell, if you start at 1, you will always be at 1. If you start at 2, you will always be at 2. Another one, which is also I will give you with the example of two-state chain, is 0, 1, 1, 0. So in this case, P to the T converges to, okay, this converges to Q, which is also 1, 0, 0, 1. Okay. I mean, but the rows are not equal. Now, if P is like this, what will be P square? If you do P square, you will see that becomes 1, 0, 0, 1. And then P cube will be again this. And then P power 4 will be again this. So all the odd powers are going to be like this. All the even powers are going to be like this. That means P to the T does not converge. So when I say matrix does not converge, I mean the entries are not converging. The entries are, for example, the 1, 1 entries alternately 0, 1, 0, 1, 0, 1. It's not converging. So whatever I wrote here, we observe numerically. It's always a very good idea to do things on a computer, see what you observe, and then try to make a theorem. But we can see that it's not always going to be true. So that means we have to find conditions. So mathematics is not going to be completely obvious. It's not that it's always going to happen. Under what conditions will such a statement be true? This is also something we will need to figure out. Okay, so all that is the key thing. So this is, in fact, if you get nothing else in this entire course, this is this answer to this fundamental question that in many situations, I will give the answer later. In many situations, this P to the T converges to this Q. This is really the fundamental theorem of Markov chains that you should know and what it means. That's all. That's what you need to know. Okay. So let's do an example. Let's work out an example of two-state Markov chain. So let's start with a two-state Markov chain. Let's see if we can work out in this situation what happens. So let's take P to be 1 minus alpha, alpha, 1 minus beta, and beta. And I will take, if alpha is 0, what happens? This becomes this matrix, first matrix here. When alpha is 1, it becomes this matrix. These are problematic cases. So I will assume that, sorry, when alpha and beta. So I'll assume both alpha and beta are between 0 and 1. Okay, to avoid that kind of problem, let's take alpha and beta to be between 0 and 1. Now, what happens to this P to the T? Can I calculate? How do I calculate P raised to the power T? Okay. In fact, you can say the basic question is just this. How do I raise a matrix to a high power? There is a very nice answer. Okay, it is which we will do. So most of you would have seen some matrix theory, linear algebra. Suppose we can diagonalize P. Suppose I can write P as X D X inverse. Okay, where D is a diagonal matrix. then everything is simple. It does not even have to do with two states. What will be P square? Will be XD X inverse. Then you will again multiply XD X inverse. So this X inverse X cancels and you will just get X D square X inverse. So what will be generally P to the power T? If you raise to the power T, you will write this T times XD X inverse, XD X inverse, XD X inverse. All this, if I do one more time, I'll get X D cube X inverse. In general, P to the power T is X D raised to the power T X inverse. Okay. Now, nice, because it's diagonal matrices I can raise powers of. What is D to the power T? It is just D1 to the power T and D2 to the power T. It's practically a pleasure to raise diagonal matrix to a power. The difficulty is when your matrix is not diagonal, then we don't know how to do. But what it is saying is if you can diagonalize P like this, then, and if you find the X and D, then it's very simple. You just raise the diagonal matrix to the power T, and then you multiply by X and X inverse, and we will be done. Okay? So can we do that? For the two-state Markov chain, we can do that. It's not true that all matrices can be diagonalized. That will be a problem. So we will have to see how to overcome that. But for now, when we are in the two-state situation, we can do it, and I will tell you how to do it. So for this matrix, so what is this X and what is the X inverse? Okay. So what is XD and X inverse? Okay. Of course, I cannot see it, so I did the calculation before coming. So I will write down the answers. Yeah, what did I write? Somewhere. Yeah, so it is the diagonal entries are going to be 1. This diagonal matrix will be 1 minus alpha minus beta. Okay. And this X matrix, this is the D matrix, and this is the X matrix that I want. X matrix is going to be 1, 1, alpha minus beta. And this will be the inverse of it. And 2 by 2 matrices are also nice to invert. So this matrix, the inverse will be what? So this will be just 1 alpha, 1 minus beta inverse. Let me write it like that. This is X inverse. So what will be this? This is P. So what will be P raised to the power T? Will be, as we said, it will be just this 1 alpha 1 minus beta. X will remain as it is. You raise D to the power T, which is 1, and then 1 minus alpha minus beta to the power of T, and 0 and 0 here. Okay, and then we have X inverse. Now let me write down also what is X inverse. X inverse turns out to be, it's not easy to, not difficult to do a 2 by 2 matrix inversion. The D comes here, A comes here, then minus alpha, that is alpha, 1, I think. There the entries get interchanged. It is, this will be alpha, comma 1 or minus 1. No. Beta, no, this will be, these will be, I think this will be minus 1. And then there is a 1 over alpha plus beta. Okay, 1 over alpha plus beta times this. Okay, this algebra you can check. I have done this before and I'm writing it, copying from my note. And it is, one can do this, but once you have this, you can just multiply and see. So when you multiply these matrices, you just have 3 matrices to multiply. What do we get? Okay, first of all, we might as well take the limit here. What happens as t goes to infinity? as t goes to infinity, these matrices are not changing. But what happens to this entry? Now, alpha and beta are between 0 and 1. You remember, alpha and beta is between 0 and 1. So, alpha plus beta will be between 0 and 2. So, 1 minus alpha minus beta. So, alpha plus beta is between 0 and 2. So, 1 minus alpha plus minus beta will be between -1 and +1. So, when I raise it to a large power, that will converge to 0. So, in the limit, it becomes very simple, and I get this matrix 1 over alpha plus beta and this. Now it's a matter of multiplying these three matrices. When you do it, you will get the answer. What happens when I get this? I get 1, 1. Yeah, so this turns out to be beta over alpha plus beta, alpha over alpha plus beta, and then alpha over alpha, again, beta over, same row will come, and alpha over alpha plus beta. Okay. So this, I have maybe skipped a couple small algebra steps, which you can do yourself later. So in this case, we do get P to the T is converging to a certain matrix Q. We are actually proving what we saw here on the computer, that P to the T is actually converging to a matrix in which all rows are equal and row sums are 1. This is our Q matrix. So what is this telling us? That P to the T, so if the two states are 0 and 1, let's call it 1 and 2. Okay, states are 1 and 2. Then P to the T 1 converges to beta over alpha plus beta. And even if you start from state 2, that also will converge to the same. Whereas P to the T 1 comma 2 converges to alpha over alpha plus beta, and P to the T 2 comma 2 will also converge to alpha over alpha plus beta. So that means it doesn't matter where you start, with probability to be in state 1 is beta over alpha plus beta. Probability to be in state 2 is alpha over alpha plus beta after a very long time. So let's go back to the numerical and see if this is correct. Here, what did I take? I took alpha to be 0.5, beta to be 0.7. And what are these numbers? If I do A, B, what should be there? What should they be? B over A plus B and A over A plus B. These are the two numbers I want. See, this 0.5833 is what we saw here, 0.5833. So you change it to something else. So just cross checking that what we have now proved is correct just against numerics. So if I change it to 0.6 and let's say 0.27 something, I changed. So I got some completely different numbers. You see that those numbers are precisely B over A plus B and A over A plus B, right? You see that it is matching. So that means in the 2 cross 2 case, we have solved our problem. We have shown, except when alpha and beta can be 0. This is when alpha and beta is strictly between 0 and 1. We have shown that P to the T converges to a matrix with equal rows. And we have also found what those entries are, because one of my questions is how to find, even if this is true, even if this phenomenon is true, how do I find these pi's? That is not obvious. And we have said that in 2 cross 2 case, we can find this. Okay. And we should also cross check against common sense. Why is this like this? So remember, we are going from state 1 to state 2. State 1 to state 1, we stay with probability 1 minus alpha. We go with probability alpha. State 2 to state 1, we go with probability beta, and we stay with probability 1 minus beta. Okay. Now, if beta is large, let's say if beta is large, what happens? That means from state 2, you are quickly running away to state 1. If beta is, let's say, 0.99, that means you don't stay at 2 very often. You just come back quickly to this. That's why when beta is large, you are more likely to be at state 1. Okay. And when alpha is large, you are more likely to be at state 2 because that's how it works. Okay, so this is the complete solution to the situation. And the point is, so, okay, so to summarize, it's 106. So I will stop now in a minute just. So the conclusion is, we have solved the 2 by 2 case. Two-state situation we have completely solved. Why? Because the other cases you can work out, okay, I have when alpha and beta can be 0, you can work out those cases. We have completely solved the two-state situation. And in fact, it looks like maybe this is also solve the higher case, because if we can diagonalize, we can use the same tool. But one of the problems is that sometimes matrices need not be diagonalizable. That can be a problem. And we will do that next lecture. So next lecture, we will give a complete solution that under what conditions this situation is true, that P to the T converges to a matrix with equal rows. Not only that, how to compute these pi's. We don't have to take limit. We can compute pi's directly from knowing P, and how to compute that. All that we will answer in the next lecture. Okay, so that will completely answer this, what I am calling the fundamental question of long-term behavior of Markov chains. Okay, I will stop here.
Yeah, thank you, sir. Very wonderful lectures. There are many questions, sir.
Yeah, sure. We can take a few. Yeah, or all. I don't know. So on the chat, or so
Yeah,
where?
here. Actually, it is on the chart. You can
Yeah, I am opening the chat. I am forgetting where
questions
we
here
stopped
only.
last. This could we use central limit that we stopped?
Only few that.
So there is next question. Whether this phenomenon of all rows becoming same always happens. As I showed, it does not always happen. Okay, that's answered. What is the name given to the matrix whose all rows are identical? And I don't know a name for that. It's really a rank 1 matrix if you think about it. If all the rows are equal, it's a rank 1 matrix. Okay, so that's all. I don't know any other name for it. Can we say entropy needs to be a certain value for pi ij to be equal? Okay, I don't want to get into entropy. I don't see the relevance of directly of entropy is important, but I don't see pi ij being equal. Okay, I do not see the meaning of this question fully. Maybe someone can ask Daksh Arora. Okay, and then looking like transition matrix P should be at least singular. That is not necessary. So if the matrix does not have to be singular. So in these cases, this matrix is non-singular. So you look at this matrix, what is the determinant of P? So I am showing you on this simulation. So I had a 2 by 2 matrix, which is non-singular. And so it is not true that P is not singular. The limiting matrix is rank 1. That will be singular, but not the P itself. Okay. So what is this comment? Diagonalize. Yeah, if we can diagonalize, good, but not all matrices are diagonalizable. So we will worry about it next time. Next, what if the transition matrix is unknown? Now that is we are working as a modeling. I mean, we have P and we are saying this. So if you come from statistics point of view, the question could be, I don't know what the matrix is. By looking at data, I believe this is a Markov chain. I can only see data. Can I deduce what is the transition matrix? That could be meaningful question in statistics. But in our situation, we always have a transition matrix. Okay, and we are going to apply that. So for us, transition matrix is kind of known. At least reasonably, we can write it. Okay. Okay, so next question, can this be applied to thermodynamical systems like the Carnot cycle? Okay, this I cannot answer because I don't know thermodynamics, I don't know Carnot cycle, so I don't know how to apply to them. Okay, I had seen Carnot cycle once upon a time. I don't think this is directly relevant to that. So the relevance is to a slightly different thing, that Yeah, so maybe next time I will tell what was that business of FNFS chain, what was the use of it. Okay. Okay, so how to fit real life data to Markov chains? That is itself a difficult question. So what you see is a sequence of observations. From that, can we tell what is the, so suppose I show you a sequence, okay? So maybe I will just answer in a glib way. Suppose you see this sequence of states, 1, 3, 5, 6. So this is coming from this random graph on this one, but suppose we don't know it is. We see 1, 3, 5, 6, 4, 5, 1, 3, 5, dot, dot, dot. We see a sufficiently long sequence. This is our data. Now, can we say, is it a Markov chain? And if so, what Markov chain it is? First of all, by looking at all the things that occurred, we can guess what are the states. 1 to 6 are the states here. Now, what are the transition probabilities? We can deduce from this, not exactly, but we can estimate. How do we estimate? For example, suppose you look at all the times 1 comes. Okay, 1 came here, 1 was followed by 3. Next time 1 came, it was followed by 3 again. Next time 1 came, it was followed by 3. You look at all the times 1 came and what came next. Here 1, 5. Okay, 1, 2. 1, 3. 1, 2. So you see how many times 1 came and out of which what proportion of times you went to 2. That will be the transition probability from 1 to 2. P12 is each time you come to 1, what's the chance I go to 2, right? So of all the times I came to 1, you look at the proportion of times, next step was 2. That will give you P12. Similarly, proportion of times you get 1, 3 is P13. So here itself, for example, let's take, just to show you illustrations, let's say y is this out of 136. So y is this sequence. So, okay, it will take me a little time to do it. Maybe I will not do it, but I hope the point is clear. Okay, so you can deduce, that's how in statistics you would be trying to deduce the transition matrix from the Markov chain. Okay. And then what was the how to fit real data? Next, how do these calculations go for an infinite dimensional state space? Well, okay, that's what I am trying to avoid. Okay, so matrix will be infinite. You can talk about multiplying them, etc. Again, the statement is that they become this, but there is no talking of diagonalizability, eigenvalues, etc. So that's why I'm avoiding it. There is a different way of approaching the infinite ones, infinite systems, which is more probabilistic and less matrix theoretic. But I want to take the matrix theory approach here. That's why. Okay. 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 Thank you for your good comments. So, can Markov chains be applied to particles at quantum level where particles obey Heisenberg's uncertainty principle? Okay. I do not know. This Markov chains, these are about classical things. So you can talk about a quantum Markov chain. I mean, in fact, one of the Kolmogov, when he talked about Markov chains, he said something which I will just maybe say it. I'm not exactly quoting it, but it's mysterious to me, but you can make of it what you will. He said that Schrodinger equation is like a Markov process. Basically, that's what it is. Okay, so I leave it for you to take whatever you want from here. But what we are sticking to is the probabilities. So this is a classical system, if you want, classical physical system. Okay, these are the questions on the comment page. Are there any?
There is a YouTube. There is one more question on YouTube.
Yes.
So Parnakar is asking, in general, is singular value decomposition used to compute the limiting matrix? Although
That's
even computing singular values for a higher order matrix is quite difficult.
right. No. See, it's not singular value decomposition that will be helpful. Diagonalization is about, again, spectral decomposition. For example, if a matrix was symmetric, maybe most of you know, or if not, it's the most important theorem for me in basic linear algebra, that symmetric matrices can be diagonalized. And in fact, the diagonalizing matrix X will be orthogonal. That is, XX transpose will be identity. So in such situations, symmetric, if P happen to be a symmetric transition matrix, we can diagonalize and easily do it. But in general, it's not that we cannot diagonalize, and it's not the singular value decomposition. Singular value decomposition will not help for the following reason. Singular value decomposition, if you can see, I'm writing here. Singular value decomposition consists in writing it as something like u dv. But what do I do with it? Suppose I square it. P square is u dv, u dv. Now, no cancellation of v and u will happen. This is not going to be helpful to me. When I multiply more, it's not going to be singular value decomposition will not help in doing this. What will help is the Jordan canonical form. We will do that. Jordan canonical form, and unlike the diagonalization, it's completely general, and every matrix you can do that. And then we will use the Jordan canonical form to do this high up, raising the matrix to the power. Okay. So that's kind of giving the suspense away. But if anybody wants to read up before the next lecture, that's